looking at our solar system, looking for patterns in our solar system, a really big pattern we see in our solar system is that there are two very different types of planets in our solar system. We call these planets Jovian planets and terrestrial planets. Jovian planets meaning Jupiter-like, terrestrial planets meaning Earth-like. The Jovian planets are Jupiter, Saturn, Uranus, and Neptune. The terrestrial planets are Mercury, Venus, Earth, and Mars. And we find that these are very different sorts of worlds. These are very different sorts of places. For instance, when we compare the Jovian, there are many differences between the Jovian and the terrestrial planets. It's really interesting. They're totally different sorts of worlds. In a way, I think it's kind of an accident of history that they're both called planets. They're totally different sorts of objects. I guess, looking from the Earth, Mars and Jupiter, well, they both orbit the Sun and they're big and all that. But once you start looking in detail, I mean, in a way, I almost hesitate to lump them both under the word planets. They're two totally different sorts of things. For instance, the Jovian things these are called often called gas giants. Gas giants, although Uranus and Neptune have a lot of liquids and stuff in there. On the other hand, these gas giants, meaning they have lots of gas, and then there's liquid under there, and there's some solid material in there too. Whereas the terrestrial planets, okay, so we're looking at the terrestrial planets, and these are all mostly solid, mostly rock, metal objects. Is there some liquid in there? Yeah, it's melted liquid, iron and stuff like that. But these are rock metal sorts of things. So these have solid surfaces. Mercury, Venus, Mars all have mountains, valleys, craters. These are places where you can land a space probe. You can land a space probe on Mercury and Mars and all this sort of thing. You will never hear about a space probe landing on Jupiter. What's to land on? It's mostly... And does the Earth have some gas? Sure it does. It has this atmosphere, which is about 1/bajillionth% of the Earth's total mass. It's a tiny, tiny fraction. No, the Earth's mass is dominated utterly by rocks and metals and nickel and iron and silicates and things like that. Same deal with Venus, Earth, Mars. Venus has this huge thick atmosphere, but it's still, like a quadrillionth of a percent of its total mass. On the other hand, the gas giants all have a big chunk of their mass made of gas. There may be a big chunk of liquid. There's a decent chunk of solid material. They're made of mixtures of material. What else? There are big differences between, the terrestrial planets are all close to the Sun. Close to the Sun. These are all far from the Sun. So as a result, as these are close to the Sun, these all have surfaces that are hot, and these all have surfaces that are cooler. So these orbits are closely spaced. These orbits are farther away from each other. Moons, oh jeepers. Jovian planets all have tons of moons. Jupiter has over 60 moons. Saturn has over 60 moons. The others have, Uranus and Neptune have a lot. Lots of moons. Lots of moons. On the other hand, Mercury has no moons. Venus has no moons. The Earth has one, which is kind of unusually large for our size, and then Mars has these two little tiny pathetic captured asteroid sorts of things like that. So few, if any, moons. What else? The Jovian planets all have rings. Yeah, we know Saturn has its rings. Well, Jupiter has rings too. And Uranus and Neptune, they all have rings of a sort. All have rings. The Earth has no rings. No rings. Neither does Mercury and Venus and Mars or anything like that. So there are these major differences. These are all solid sort of planets with mountains and craters and valleys and all this sort of thing. The largest of the terrestrial planets is the Earth. So these are all very small. Small. The Jovian planets are all very big. The largest of the terrestrial planets is the Earth. the smallest of the Jovian planets is Uranus, and Uranus is like 14 times the mass of the Earth. Jupiter is like 318 times the mass of the Earth. Saturn is like 95 times the mass of the Earth. And the Earth is the biggest of the terrestrial planets. You know, Mercury is the smallest. So, I mean, there's some major, major differences here. These are totally different sorts of things. You know, Jupiter is 300 times the mass of the Earth. You add up all the terrestrial planets, and it's not even 1% of the mass of, you know, Jupiter or something like that. So this is a really major, major difference. These have tons of moons. These have rings. These have all this. So the question is why? So there's a pattern. There's a pattern. This is how science works. We observe the natural world. We see patterns. And, you know, we try to figure out what they are. And then to explain those patterns, we develop hypotheses. And then when they're well tested, they become theories. So here's the question. Why two types of planets? Why two very different, distinctly, very separate types of planets? Why not three types of planets? Why not a smooth variation planets with planets slowly changing, you know, evolving from very terrestrial to very Jovian or something like that? I mean, but there isn't. You're either terrestrial or you're Jovian, and there's nothing in between except for the asteroid belt. But, you know, the two very distinct categories. So we need to explain why. So we want to explain the Jovian-Terrestrial Dichotomy. Why? So we need a theory for Jovian versus terrestrial dichotomy. Dichotomy. You're either one or you're the other, nothing in between. So, well, again, it's got to go back to history, because go back a million years and same deal, same two types of planets. It must have to do with where they came from and how they formed. Now, they must have formed together because both your terrestrials and your Jovians orbit the sun in the same direction and they spin in the same direction, so that's still there. They must have formed together, but that makes the mystery even harder. How in the world do you explain two totally different types of planets when we know from the patterns of motion that they formed together at the same time in the same place out of the same stuff? That makes it even worse. How in the world can you know, given that they formed here out of this stuff at the same time, how can you get these two totally different sorts of planets? And to understand that, we need to understand how to make a planet. So, how make planets? Skipping a few words. How do we make planets? So here's the idea. If you can make really big things like stars out of gas. In order to make a star out of gas, well, it's an issue of having enough gravity. You know, gravity pulls in, and then the heat pressure on the gas pushes outward. And so, if you have enough stuff, you can beat the heat pressure, and if it's cold enough, and then you can compress the stuff down. You can make a star. Planets are too small for that. You cannot start making a planet. So here's a key idea. You cannot start making a planet out of gas. Doesn't work. If you just have hydrogen and helium gas, these two lightest elements, these two simplest and most commonest elements in the universe, if you just have hydrogen and helium floating around, you're never going to make a planet. It doesn't work. The math doesn't work. Gravity is not going to win. So what I need is solids. Solids. Solid materials are relatively rare in the universe. Our universe is roughly like the sun. It's roughly 70% hydrogen, 28% helium, 2% other stuff. And, well, this hydrogen and helium don't turn solid under any condition. So it's got to be that other 2% of stuff. And so that's what we're dealing with. And so, you know, our solar system formed from this big spinning cloud of gas and dust. The dust is the key if you want to make planets. Because you need solids, and the solid materials in this were in the form of dust. And when I say dust, I mean really small particles. We can see this going on right now. There are other solar systems forming out there today. And when we study them, we find that these dust particles are really tiny particles. They're about the size of the particles in smoke. Really, really tiny microscopic sorts of things. Except that, well, okay, what does dust do? Dust sticks together. Dust sticks together. And what happens when dust sticks together? Well, then it sticks together and gets bigger and bigger. This explains the dust bunnies under my bed. You know, this is what this dust sticks together. It works in space too. So if you've got these tiny little particles like smoke, and then gravity's causing this cloud to contract, getting smaller and smaller, spinning faster and faster, the dust particles are more likely to stick together, so they're going to start building up bigger and bigger dust bunnies. You know, dust sticks together. The technical term is dust bunnies. No, it's not. I just made that up. But that's what we're talking about. And then once they start getting bigger, and you know, the size you can see, and then as they get bigger and bigger, then gravity starts to take over, and pretty soon you have things the size of desks, and things the size of houses, and things the size of mountains, and then things the size of continents, growing bigger and bigger. And the bigger you get, the more gravity gets in the game, pulling these, a dust bunny doesn't have a lot of mass, but as it gets bigger, other things do. Bunnies, and then, things the size of houses, and then mountains. And then, but by this time now, gravity's really compacting things together, finally things the size of continents. And then planets. So there's a very, very simple, but the math kind of works on this. If you start with tiny little dust particles sticking together, and then gravity gets more and more important. And of course the whole cloud is getting compressed by gravity anyway, and so then you can gradually, over a period of a long time, I mean, forming our solar system wasn't like, we're going to do it today. No, if you run the math, we're talking about millions of years. Not billions of years. Solar system is 4.5 billion years old, so, but on the other hand, we're still talking millions of years in order to do it, which is, a long time. So anyway, so we do this, and here's the sticker. Here's the thing. In order to make planets, you need solid things. And near the sun, the only solids, it's hot, so the only solids are rocks and metals, because it's hot. So what do you get? You get rock metal planets. So near the sun, where it's hot, the only solid things are rocks and metals, so it's hot, so you get terrestrial planets, which are mostly terrestrial planets because it's mostly rock and metal. In the outer solar system, far from the sun, there's another set of material. It gets colder, and there's another set of materials. Other materials go solid. Other materials are solid. These are the material that we call the ices. And so this includes water ice, H2O, water ice. It includes methane ice, CH4, methane ice. It includes dry ice, carbon dioxide, methane. So we've got these other materials which freeze solids. We've got ammonia, NH3. So these collectively become the ices. And then somewhere about just a little bit beyond the orbit of Mars, you get far enough from the sun that it's cold. These things freeze, and now you have ice crystals. And so what happens, so since you have more raw materials, these things are a lot more common in the universe than like iron and metal. And since you have a lot more stuff to work with, a lot more raw materials, you build bigger planets. Bigger planets. The cores of the Jovians. So the Jovians get up. So as a result of this, because they're working with more raw materials, your Jovians begin to be bigger. And then, this is, so you have Jovian cores of rock, metal, plus lots and lots of ices. There's tons more ices than there are just rock and metal. So you start getting cores of planets which are 3 or 4 or 5 times the mass of the Earth. And then it really takes over, because then you have enough gravity to hold on to hydrogen. And then grab hydrogen and helium, and there's tons of those. Hydrogen and helium are the most common stuff in the universe. Hydrogen and helium, the Earth's gravity is not strong enough to hold on to hydrogen and helium at these temperatures. You pop a helium balloon, that helium gas goes up and up and up and up into the atmosphere, and it keeps going into space, and it leaves, because the Earth's gravity is not strong enough to hold on to it at our temperatures. But you build an object 4 or 5 times the mass of the Earth, because you got tons of these frozen ices around. Now you can hold on to hydrogen and helium. And so once you can hold on to hydrogen and helium, well, there's plenty of that. And so the Jovian planets suddenly start pulling in more and more and more and more of that. And so pretty soon your 4 or 5 Earth mass core is dominated by 300 Earth masses of gas, and you have Jupiter. And then gas dominates the mass. And that's why we have 2 distinct types. That's the theory. That's the theory to explain the observed pattern that explains why we have 2 totally different classes of planets in our solar system. Near the sun, only rocks and metals are solid, so you build small rock metal planets. Far from the sun, you got the ices. The ices allow you to get a lot bigger, and they get you over the threshold till you can pull in hydrogen and helium. There's tons of that around, and suddenly you've got enormous planets whose mass is dominated by hydrogen and helium, and that's what the Jovian planets are.